Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.3. How derivatives affect the shape of a graph.
Lesson 2. Finding local maxima and minima.
So the thing that we're going to talk about next is really the transition points, the points between where a function is increasing and decreasing, or decreasing and then increasing. So what I want you to do is to look at this page. It's the 9th page. It's after all of the 3 examples that we talked about. And at the very top it says Local Extrema of f. And that's what we'll be talking about next, what are called the Local Extrema. And I want you to imagine a weird sort of imaginary mountain range that's 2-dimensional. So here's our mountain range, and this is really our curve y equal f of x. And imagine yourself walking along this mountain range. Well, if you're walking in the positive x direction but forced to go along this black curve, you notice that you're going to be going up where the curve is increasing, you're going to be going down where the curve is decreasing, and at some point you're going to get to these peaks, like this one, where you are sort of at the top of a little hill. And each of these peaks is called a local maximum. And I'll say it's called a local maximum point. So the peak point that you get to right here is called a local max. Sometimes in some textbooks it is referred to as a relative maximum point instead of a local max. They mean exactly the same thing. So here you are at a peak, and that is what's called a local maximum point. Now you might think, well, why is it called a local maximum point? I'm up here at the peak, but is there a point that's even higher on this curve? If you continued along this mountainside, you would hit another maximum here, local max, and another local maximum here. Let's label them. So we're calling this a local maximum, which we often just say local max. When you get to this point, you're at another local max. When you get to this point, you're at another peak, so that's a local max. And notice that none of these points is the highest point anywhere on this mountain range, because it looks like if you continued beyond the point x equal 20, there's an arrow on the graph, and so this mountain range would sort of go up forever in this direction. And so there are points up here that are higher than any of these maximum points that you hit, any of these peaks, and that's why they're referred to as a local maximum. It means that you are higher than all points that are close to you, nearby you, and we'll make that a little more precise in a moment. Now on this curve there are also valley points. So you keep walking along here, and at some point you're down here in the valley. Let's see if I can get my pen to work. So at some point you're down here, and it's lower, a point that's lower than all the points that are nearby you, points to your left and points to your right. And so such a point is called a local minimum point. And can you see other places, other x values where there are local minimums on this imaginary mountainside? It looks like there is one at 15. So let me label this as a local min. And this one is another local minimum point. And yeah, it looks like there's one here at 20, would be another local minimum. And all that we mean by that is it's a valley point. If you're standing right here, you are lower than all points to your left or right. When you're at a local maximum, you are higher than all points close to you that are to your left or your right. So let's try to define local maximum a little bit more precisely by looking at this picture that's right here. I can see from the picture that this does look to be a place where I would have a local maximum, and it's at a point corresponding to an x value of c. And so when I plug c into this function, I get f of c as an output. And perhaps, just to make it very clear, that means the height under the curve right at c would be a height f of c. And you notice that if I pick an x value that's close to c, if this is a local maximum, if I pick an x value, say here, and figure out the height under the curve at that point, I'm going to call that would be f of x. You notice that f of x is smaller than f of c. So if this is a peak point, it's going to be a point where the output value of the function is greater than the output value for nearby points. So technically what we say is that f has a local maximum at an x value of c if f of c is greater than or equal to f of x for all x near c, and I put near in quotes there. Technically what that means is that we can find some open interval of x values around c, and that's what this red interval is here. That if you pick any x in that red interval, the height under the curve at those x's will be less than or equal to the height right at this local maximum. So that's the technical definition of local maximum. And local minimum has a similar definition. F has a local minimum at c if, well, what would have to be true about f of c at a local minimum compared to f of x for all x, I'll put in just quotes again, near c, meaning in some open interval around c. These heights, if it's a local minimum point at c, and you figured out the height under the curve was f of c, then when you look at a nearby x value, you notice that the height under the curve at a nearby value is going to be larger than the height at your minimum, at your local min. So we would say f has a local minimum at c if f of c is less than, see if I can write that correctly, I'll put it in purple, less than or equal to f of x for all x near c. So those are the technical definitions of local max and local min. And in general, we say that if f has either a local max or a local min, one of those two, we have a general term to talk about local max and local min as a group, then we say f has a local extremum at c. So a local extremum means either a local max or a local min. Okay, let's go ahead. Oh, one other thing I wanted to mention before we leave this is that local max and local min are kind of slightly imprecise terms. So I'll just mention that, maybe I'll write it right here, that we talk about a local maximum point, and we talk about a local maximum point. What we will mean by that is having both the x and the y coordinates c comma f of c. So this point right here would have coordinates, x coordinate c and y coordinate f of c. So that would be the local maximum point. Sometimes we talk about a local maximum value. And by a local maximum value, we really mean the output value of the function at that local maximum point. So the local maximum point would have the x and the y coordinate. The local maximum value is really just the y coordinate. It's the output. So that's like the biggest output that that function gives for all points near c. So local maximum value is f of c. Local maximum point is the point c comma f of c. So I just mentioned that, and sometimes we say local max, and you just sort of have to get from the context whether they're talking about a local maximum point or a local maximum value. We're a little sloppy when we talk about it. Okay, let's go ahead and look at the next page. That's great. We've discussed what the local max and the local minimum of a function are. I've drawn exactly the same graph y equal f of x again here, but now the question becomes, how do we find the local maximum and minimum if we're not given the graph of the function, if we're just given the equation of the function. So that's what we're going to discuss in this page and on the next page, is how to find the local max and min. Well, let's start out with a scenario where we are given the graph of the function y equal f of x. And what I want you to notice is that one of two types of things happen at a local maximum point or a local minimum point. If we look at, say, the point x equal 5, we know that that's a local maximum point. And what could you tell me about the slope of the tangent line right at that point? It looks like the slope of the tangent line just to the left of 5 would have a positive slope. The slope of the tangent line to the right of the 5 would be negative. But right at 5, it looks like you have a horizontal tangent line. And so what would the slope of that be? Slope of a horizontal line is 0. And remember that the slope of the tangent line is exactly the same thing as the derivative. So the derivative of this function at 5 would end up being equal to 0. It's just the slope of the tangent line to the curve at that point. If we go to x equal 10, that's where we had a local minimum point. It was a valley point. And notice the same thing is true, that the tangent line there would be horizontal, and so the slope of the tangent line, which is the same thing as the derivative at that value 10, would end up being equal to 0. So one of the things that can happen at a local max or a local min is that your derivative could be equal to 0. Is that always true at a local max or a local min? Let's look at 13. That was another local maximum point. It's higher than all points nearby it. Is it true that the derivative is 0 there? Well, unfortunately, this has a sharp change in the tangent lines. As you come into 13 from the left side, you have a very large positive slope for your tangent line, and just to the right of 13, it looks like you have a large negative slope. There's an abrupt change in the derivatives right at that value of x equal 13. And remember, we said that when you have a sharp corner or a cusp, your function is not differentiable at such a point. So this is exactly a point where the derivative at 13 would be undefined. If you were to try to find the limit as h approaches 0 of f of 13 plus h minus f of 13 all divided by h, you would find that that limit does not exist, and so we say the function is not differentiable there. So that's the second type of thing that can happen at a local max or min. So one of two things can happen at a local max or min. Either the derivative is 0, as it was in these first 2 points, or the derivative is undefined. I'd like you to look at the other local max and min in this picture and decide for a moment for yourself whether those are points where the derivative is 0 or whether they are points where the derivative is undefined. So pause the tape for 30 seconds and just decide at each of the other local maxes and mins what's happening to the derivative. Okay, so I'm hoping you had a chance to think about these other points. At x equal 15, right here, I have a sharp corner, a sudden change in the slopes of the tangent lines. Remember, sometimes what we say is at such a point there's no unique tangent line. There's no way to draw a line that follows the curve closely that's unique. So at 15, that would be another place. This was at 10. That would be another place where the derivative is undefined. So f prime of 15 would actually be undefined. So that's what's happening at that local min. At this local max, let's see, it looks like a nice smooth curve through there. So it does have a unique tangent line. The tangent line is horizontal, so f prime of 17 would be equal to 0. And at 20, again, it looks like a nice smooth curve. There is a unique tangent line there. It just happens to be horizontal. And so f prime of 20 would also be equal to 0. But one of those two things happens. I'll put down here what's true about f prime at the max and min, meaning the local max and min. Either f prime of x is equal to 0, or the other possibility, f prime of x is undefined. So one of those two things happens. So we can go ahead then and write down kind of a general theorem here, just summarize what we've learned so far. If f has a local extremum, and remember a local extremum is either a local max or min, if it has a local extremum at C, then one of these two things is true. We could say f prime of C is equal to 0, or f prime of C is undefined. And all that's really saying is that there's really two types of peaks and valleys. Either you can have sort of a smooth peak like this or a smooth valley like this. That'll be a place where the derivative is 0. Or you have a sharp peak or a sharp valley, and that'll be a place where the derivative is undefined. And that's all we're really saying in that theorem. Well, a definition, and we actually already used this word before, so I'm going to remind you about that as we go back to our example 1, 2, and 3 in a moment. We call the C values where f prime of C is 0 or f prime of C is undefined, those are called the critical numbers, or sometimes they're called critical values. I'll put that in parentheses, so we kind of use those words interchangeably, of the function f. So if we were to look for all the places where the derivative is 0 or where the derivative is undefined, those would be called the critical numbers of our function f. And as we go back to example 1, 2, and 3, remember we called the places where the derivative could be changing sign the critical numbers. And as we go back, I'll show you that those are in fact exactly the numbers that make either the derivative 0 or make the derivative undefined. One thing that I want to mention, which is kind of important, is this question that's down here. This theorem says if you have a max or min at C, then f prime is either 0 or f prime is undefined at that C value. But the question down here is, does our theorem work in reverse? In other words, if your derivative is 0 or your derivative is undefined, does that implication go in the other direction? Does it mean we have a local extremum, in other words, a local max or min at that point? And the answer is no. This theorem works in this direction. If you have a max or min at C, then f prime of C must be 0 or it's undefined. But the reverse, unfortunately, doesn't work. And to see some examples of that, you could think about a function that maybe looks something like this. Try not to make that too sharp there. But if it looks like this right at C, and gets really, really steep right at one point. See if I can get my pen to work again. If it gets really, really steep right at C, you notice that there will be a unique tangent line there. But what's true about the slope of the tangent line right at C? If it's a vertical line, the slope of a vertical line, remember, is undefined. So this would be the same as the derivative at C, but unfortunately the slope of a vertical line is undefined. So this would be a critical number of f. It's a place where the derivative is undefined. So that's a critical number. Is it a local max or a local min? If you thought about somehow standing right at this point where the mountainside becomes vertical, you'd have to ask yourself, well, are all points to my right and my left lower than me? If I'm higher than all nearby points, both to my right and my left, then this would be a local max. But that's not true. There are points that are higher on the right side of C and lower on the left side of C. So it's not a local maximum because it's not the highest point of all nearby points. There are points to the right that are higher than the point right at C. It's also not a local minimum. If this were a local minimum, then the points would have to be higher than you on both sides. They're higher than you on the right, but they are not higher than you on the left. So just notice this is not a local max or min. and yet the derivative is undefined. And you can think of other cases too. Maybe this is an easier case to visualize when you have a hillside that looks like this and it gets very flat right at C. If you thought about the tangent line at C in this picture, you notice that the slope of the tangent line, which would be the same thing as f prime of C, see if I can write that in there correctly, f prime of C. Well, what would that slope be? That would be a slope of 0, because here the tangent line is horizontal. But again, if you thought of standing right here on the mountainside and you ask yourself, is this a peak or a valley? It's neither of those. It's not a local maximum point because there are points right next to you that are higher. And it's not a local minimum point because there are points right next to you that are lower. So this has a derivative of 0, but it is not a max, a local max, or a local minimum. And you can even draw a graph that looks something like this, very steep straight line coming up to C, and then a slightly less steeply slanted line beyond C. If you think about the derivative right at this point corresponding to C, because there's a sudden change in the slopes of the tangent lines, f prime of C is undefined. So that's a critical number. It's a place where the derivative is undefined. But again, if you thought about standing right here, it's not a peak or a valley. It's not a maximum because there are points just to your right that are above you. And it's not a local minimum because there are points just to your left that are below you. So again, this is a place where it's a critical number, but it's not a max or a min. It's not an extremum. So this theorem does not work in reverse. If f prime of C is 0 or f prime of C is undefined, it doesn't necessarily mean it's a max or a min, but if it's a max or a min, it does imply that either the derivative is 0 or the derivative is undefined. Well, what does that mean for us? It means that if we find the critical numbers of a function, so we take its equation and find all the critical numbers by finding all the x values for which the derivative is either 0 or the derivative is undefined, we'll get a big bunch of x values, and among those x values must lie all of the local max or min. Some may be neither a max nor a min, but if there are any max or min of the function, if you're looking for where all the peaks and valleys of the function are, they must be among these critical numbers. So the procedure that we're going to use in order to find the peaks and valleys of a function is going to start with finding the critical numbers, and then we'll have to test each of those to decide, does that critical number correspond to a local max, does it correspond to a local minimum, or perhaps it is neither one of those, like these weird situations that we talked about down here. Well, let's turn to the next page and we'll talk about the test that we will use to determine whether a critical number is a max, a min, or neither. So on the next page it says to find the local max and min, first we'll find the critical numbers. So we'll find all of the x values for which the derivative is 0 or the derivative is undefined, and then we'll decide whether each one is a local max, a local min, or neither. And it may contain any combination of those. You may not have any local max or min. They may all be other sorts of points. But then the question becomes, well, how do I decide whether each one is a local max, a local min, or neither? And we're going to use what's referred to as the first derivative test to determine this step 2, what type of point we've got once we find our critical numbers. Let me point out that the first derivative test only works in the case that f, I'll put f, must be continuous at at x equals c for this first derivative test to work, and we're assuming already that we've found c numbers, c values for x where the derivative is 0 or it's undefined. So we're assuming that we're looking at our set of critical numbers, and we'll take each one and apply this test to it and decide, gee, does this c correspond to a max, to a min, or neither of those? So let's see how that first derivative test works. And what I want us to do first is just assume we have a picture like this. We know c is a critical number. For example, maybe c is a place where the derivative is equal to 0, or it's a place where the derivative is undefined. And suppose that further I look at the derivative f prime of x and I test its sign to the right and the left of the c value. And when I plug in values that are to the right of c, perhaps the derivative turns out to be negative. And when I plug in x values that are to the left of c, perhaps the first derivative turns out to have a sign that is positive. Remember that we said back when we were doing our example 1, 2, and 3 that knowing something about the sign of the derivative tells us something about the graph of the original function f. If the first derivative is positive, what does that mean about the graph of f? We said that means that that graph must be increasing. And if the derivative is negative, that means the graph of f must be decreasing. So what does my function have to look like up here? Well, right here, if the derivative were 0, for example, we would have a horizontal tangent line right there. And we know that the function has to be increasing up to that point and then decreasing beyond it. And we'll assume that f is continuous at and near c. So we would have a function that would have to look something like this. It's going up until I get to c, has a horizontal tangent line right at c, and then we know that it is decreasing after c. So if we had this sort of scheme, and all of these things are things we could find out just from the equation of f of x, then what would we know about this point? It looks like it would have to be a local maximum. That's the only way it could be increasing to the left and decreasing to the right. Well, let's suppose we have the same scenario where f prime of c is a place where it's equal to 0. And I tell you now, when you go ahead and you test the sign of the derivative f prime of x, you find that it's positive to the right of c and it's negative to the left of c. Well, what would that mean about the function f? If its derivative is positive, then the function must be going up. If its derivative is negative, the function must be going down. And so what would the graph up here have to look like? Well, we know we have a horizontal tangent line right at c because the derivative is 0 there. And we know that the function is going down till I get to c, going up after c, and we're assuming that it's continuous. I shouldn't say continuous at x equals c. I should say continuous maybe in an interval of values around x equals c. So at c and also to the right and the left of c. So I'm going to assume that it's continuous, and I can draw a continuous graph through here. If it's going down, hits this point, and then goes up, it's got to be a graph that looks like this. And what kind of point would this be? This would have to be a local minimum. So we find the critical number, and then we just test the sign of f prime to the right and the left. If the curve is going down and then going up, this must be a low point. It must be a min. If the curve is going up and then down, this must be a high point. It must be a maximum. Now, on the other hand, suppose we have the same sort of situation that we find the derivative, we find the critical values, and we find that the derivative is equal to 0, say, or undefined. Same type of argument will hold if f prime is undefined. And I test the value of f prime to the right and the left of c, and I plug in an x value to the right of c and find out that f prime is positive, and I plug in an x value to the left of c and find that it's also positive there. Remember, what would that mean about f? It means that it's increasing to the left of c, and it continues to increase to the right of c. If you thought about the type of graph that would go along with that information, well, we know that the tangent line is horizontal right at c because f prime of c is 0. We know that the function is increasing to the left of c, and then it continues to increase to the right. It would have to be a function maybe that looks something like this, that gets real flat right at c, but it's increasing to the left, but instead of going down, it continues to increase to the right. Now I want to ask you, what type of point is this? Is it a local maximum or a local minimum? This is the type we talked about at the end of the previous page. If you're standing right at this point, it's not a local max because there are points right next to you that are a little bit higher. And if you're standing right at this point, it is not a local minimum because there are points right next to you, to your left, that are lower than you. So this is a case where it's neither a local max nor a local min. And the same type of thing would hold if you know that f prime of c is equal to 0 and f prime of x is negative on both sides of c. Then your function must be decreasing to the left of c, continue to decrease to the right of c. And so you must have a situation, let's see, we have a horizontal tangent line right here. It's decreasing and then continues to decrease. So it would have to be a graph that looks something like this. Gets real flat right at c, but then it continues to dive down. And again, this would be neither a max nor a min. That's how the first derivative test works. You find all of your critical numbers, places where either the derivative is 0 or it's undefined. In our examples, I made the derivative 0 each time. It's just a little simpler, but the same exact argument works if f prime of c is undefined. And then to decide whether each is a local max or min, you check the sign of f prime to the right and the left. And that will tell you if the curve's increasing and then decreasing, it must be a max. If it's decreasing and then increasing, it must be a min. And if it has the same sign on both sides, then it's neither a relative max, a local max, or a local min. Well, this is sort of all in theory. Let's see how it works on an actual example by turning back to our example 1. And now we're going to go through example 1 part B, example 2 part B, and example 3 part B, and see if we can apply this first derivative test to actual functions. And I think you'll see that it's actually pretty simple when you look at the actual example. So I'm turning back, it's really the third page of this section, to the example f of x equals 3x to the fourth minus 4x cubed plus 1. This one we did part A on, and I want to remind you briefly of what we did in part A when we were trying to decide where f was increasing and decreasing. Remember, we found the derivative. Derivative was 12x cubed minus 12x squared. We factored it, and we said, well, at what values of x could this expression be changing sign? And we said it's wherever this factor is 0 or this factor is 0. And we found the first factor was 0 when x was 0, and the second factor was 0 when x was 1. Those values of x where this is changing sign are exactly the critical numbers that we just defined. In this case, because the derivative itself is a polynomial, it's defined everywhere, and these critical numbers that we found are values that, if I plug them in, would make the derivative equal to 0. Remember, critical numbers we defined a little more carefully in those last couple of pages that we just discussed as places where either the derivative is 0 or the derivative is undefined. And for this particular example, because the derivative is a polynomial, it's never undefined, so we don't get any of those kind of critical values. But we can find values that make the derivative 0. And those are precisely, the critical numbers are precisely the places where the derivative could be changing sign. So they're exactly the numbers that we found when we were going through part A of this. So we found our critical numbers, and we also did a sign chart for f prime. So now let's go ahead and try to answer part B. Find all the local maxima and minima of this function. So let's go ahead and use the sign chart that we already developed in part A. 0 and 1 are our critical numbers, and step 2 in finding the local max and min is just to decide whether each of these is a local max, a local min, or neither. So we'll concentrate first of all on x equals 0. So let's think about that one first. And if you want to, you can sort of think of covering up the rest of the sign chart, at least mentally in your mind, and concentrate on the sign of f prime to the right and the left of x equals 0. Notice that f prime is negative to the left and continues to be negative to the right. We already said that means the function is decreasing to the left of 0 and just continues to decrease to the right. So what does that graph have to look like? Well, that's got to be something that's, going down till we get to 0 and then just continues to go down. It gets really flat in here at 0, but it continues to go down to the right. And that point then is neither a maximum nor a minimum. It's not a low point, it's not a valley, it's not a high point, it's not a peak. So there is neither a relative, or I should say a local maximum, nor a local minimum at x equals 0. If you wondered what point you were talking about on the graph of this function at 0, 0 is the x-coordinate of the point, and if you're talking about a point on the graph of the original function, then to find the corresponding y-coordinate, you'd want to plug into the original function. So if you wanted to know what point we were talking about on the graph of f, you could just find the corresponding y value by plugging 0 into this function. And if I plug 0 into this function, f of 0 would be 3 times 0 to the 4th, that's 0, minus 4 times 0 cubed, that's 0, plus 1. So the y-coordinate at this point would be 1, but that point 0, 1 is a point on the graph, but it's neither a max nor a min. All right, let's concentrate on the other critical number that we looked at, x equal 1. And again, if you want to, you can sort of think about just covering up the portion of the graph that involves the other critical number so that you can concentrate just on x equal 1. And we said the sign of f prime was positive to the right, it was negative to the left. That meant the function was going down to the left of 1, then turns around and goes up to the right. And the only kind of function that could do that would be one that has a valley point right at x equal 1. It's going down, then it's going up. So as long as your function is continuous, and it is, it's a polynomial, it's continuous everywhere, then this must correspond to a local minimum point. So we must have a local min right at the point corresponding to x equal 1. Well, what is that point on the graph? The x-coordinate is 1. If I want the corresponding y-coordinate of a point on the graph of f, I have to go back and plug into f of x. And I think I actually did that up here. I plugged 1 into the function, and I'd get 3 times 1 to the 4th, minus 4 times 1 cubed, plus 1. That'd be 3 minus 4 is negative 1, plus 1 is 0. So I believe the y-coordinate on the graph of f that corresponds to x equal 1 would be 0. So we have a local minimum at the point, at the point 1, 0. And there are no local max. Remember that if we look for the critical numbers, and we did that, all of the local max and min that exist for this function must be among these critical numbers. So if there were going to be a local maximum for this function somewhere, then there would have had to be a third critical number where that local max occurred, and that doesn't happen. We only found these two critical numbers. One of them turned out to be neither a max nor a min, the other one turned out to be a min. Well, before we leave this example and go on to the next one, what I want us to do is the next step that I would do if I were trying to eventually graph this function. We haven't talked about what's called the concavity of the curve yet, so we can't draw a really accurate graph of f of x, but we can go ahead and use the information we've learned so far to draw what I call the very rough sketch of f. And all we're going to do in this sketch is draw kind of a dotted line that shows where the function's going up and where the function's going down. The 2 points that we found so far in our graph, we found this point 0, 1 was a point on the graph. Let me just kind of mark that in here. And we found that 1, 0 was a point on the graph. This one turned out to be neither a max nor a min, but this one was a relative, or I should say a local minimum point. And remember from our sign chart, I'm going to put that back here for just a moment, our sign chart told us where the function was going down and where the function was going up. We said the function is decreasing to the left of this point 0, 1. It continues to decrease to the right. It has a valley point, local minimum at 1, 0, and then it starts increasing again. So I'm going to try to translate that over to my graph and just say what's happening very roughly on my graph. To the left of x equals 0, the function is going down. It continues to go down to the right. Remember, this was neither a max nor a min. And it continues to go down until it hits this local minimum. And then what happens? Then the function starts to go up again. So it's basically decreasing until I get to this local min, and then it starts increasing after that. So from that point on, the function just begins to increase again. Now, the actual graph of f of x won't look quite like this. We haven't dealt with what's referred to as the concavity. It's sort of how it's curving as it goes down and how it's curving as it goes up. But we do have the overall behavior, the rough behavior of the graph. We know it's going down till it hits this local min, and then it is going up forever from that point on. So we keep that in mind because we're going to add more detail to this graph, but it's helpful to have this kind of dotted line here so that when we add in more qualities to our graph, we don't lose sight of the fact that our graph, our final graph, which we'll do down nicely down here eventually, must be going down till we hit this point and then going up. Whatever else happens, we cannot alter that. Okay, let's go to example 2 and see if we can do part B of example 2, namely locating all of the local max and min on our second example. So if you flip back to example 2, remember that was the cube root of the quantity x minus 1 squared. And we actually already did all the work that we need to do for part B here to answer this question, find all the relative max and min. I kind of use these interchangeably because they use different words in different textbooks. It's the same thing as local max and min. We already found all the critical numbers. I want to just mention for a moment that the critical number we found f prime, it was this, 2 over 3 times cube root of x minus 1. We found the critical number was x equals 1. And notice that's a place where my derivative is undefined. Before we said the critical numbers are just the numbers where this expression for f prime could be changing sign. But in particular, this critical number is a place that makes the denominator of my expression 0. So f prime of 1 would be a place where the derivative is undefined. F prime of 1 would be undefined. But that's just one of my critical numbers. It's just anywhere where this could be changing sign. So it's anywhere where a factor in the numerator of a fractional expression or the denominator of a fractional expression is undefined. So we found our critical numbers, so we did that already, and we did a sign chart. So we put this on a number line, and we found the sign of f prime to the right and the left of the one and only critical number. Okay, so what did we find out? We found f prime was positive to the right of 1, negative to the left of the 1. That meant the function had to be going down to the left of 1 and up to the right of 1. And you can almost see if you just connect these arrows in your mind what kind of point 1 has to be. X equal 1 must correspond to a valley point, to a local minimum value. So there was only one critical number in this case. And it looks like, because the curve is going down and then going up, that it must correspond to a local min. So I'm just going to write in here local min. And if I want to know the coordinates of that point, remember to find the corresponding y-coordinate for x equal 1, we always plug back into the original function because we're trying to find a point on the graph of the original function. That's our whole goal, is to be able to graph this original function. So you're just plugging into f, and if I plug 1 into f, well, 1 minus 1 would be 0. Square it, I get 0. Take the cube root of 0, I get 0. So the output value is 0. So we would have a local min at the point 1, 0. That's kind of an interesting coincidence because we had a local min on the last example at 1, 0, but that's just a coincidence. Let's go ahead now and draw a rough graph of f of x. So if you turn to the next page, you'll notice that there is a place there, a set of axes for us to graph f of x. I only drew one set of axes here, so we'll draw our rough sketch and our final sketch on the same graph. But what we just said, and I'm just looking back at what we just did over here, we said there's a local minimum at 1, 0. So on this graph, here's 1, 0, and I know I have a local minimum at that point. And we said that the function is decreasing until we get to that local min, and then it's increasing. There are no other local max or min anywhere. If there were, we would have found more critical numbers, and we only found x equal 1 as a critical number. So we know roughly that the function is going down till we hit that minimum, and then it's going up after that. And of course, this isn't a very accurate graph. We have only one point that we've actually plotted, but we do know exactly where this function is turning around from being decreasing to increasing. So one of the wonderful things about calculus is you can find that exact point where it switches from decreasing to increasing or vice versa. You can find these exact local max and min. Okay, let's look at example 3 and do exactly the same thing. For example 3, we talked about this function that involves the exponential function, the natural exponential function. Remember that f of x was x e to the minus x. And we took the derivative. We had to use the product rule and the chain rule to find the derivative. We rewrote the derivative, and here it is in the fractional form. It was 1 minus x over e to the x. We said the denominator is never 0. And that's because e to the x is always a positive value no matter what x you plug in. So this derivative is never undefined because its denominator never goes to 0. But we did find a critical value where the numerator was 0. So that'd be a place where the derivative equals 0, and that was at x equal 1. So we found one and only one critical number, x equal 1. We did our sign chart, so we found that the derivative was negative to the right of 1. It was positive to the left of 1. And we said that means the function is increasing until I get to 1, and then it is decreasing. So what does that mean about x equal 1? What kind of point is that? A local max, a local min, or neither of those? If the function's going up and then it's going down, if you just think of connecting these green arrows in your mind, the point right at x equal 1 must be a high point. It must be a peak. In other words, it must be a local maximum. So x equal 1 was our only critical number, and we've just seen from our sign chart that it must correspond to a local max because the function is going up to the left, going down to the right, so that must correspond to a high point, a peak. Well, how do I find the coordinates of that local max? The x-coordinate is 1. The y-coordinate, I want to point on the graph of my original function, so the y-coordinate I get by just plugging 1 into the original given function. So let's see what that would be equal to. Well, I'll do it down here. F of 1, if I plug into the original function, is 1e to the negative 1. So that would be 1 times e to the negative 1, same as 1 over e to the positive 1. So that would actually give me 1 over e for the corresponding y-coordinate. So when x equals 1, f of 1, in other words, the y-coordinate is the number 1 over e. So we have a local max at the point 1, comma 1 over e. And remember, e is just a number. It's about 2.7. I think I even figured out approximately what that was with a calculator, if I can find my notes. Yeah, it turns out that that's approximately, well, the x-coordinate is 1 and the y-coordinate is approximately 0.37. Just for graphing purposes, it's nice to throw 1 over e into a calculator and figure out what that's roughly equal to. Well, let's do the same thing we did on our other examples, and let's go ahead and draw the rough sketch, the overall up and down behavior of our function. So I'm going to kind of push this off to the side, and here's my axes down here, and at 1, so I go over to x equal 1, and the y coordinate was, so it was at, at 1 comma 1 over e, which is approximately 1 comma 0.37, we have a local max. And so let's see, if this is 1 on the x-axis and this is 1 on the y-axis, I want to go up a little more than 1/3 of a unit, so it'd be maybe right about here. That might be a little bit too high. And so I don't really know any other points on this function, but I know that it is a local max. So the function is going up until I hit that point, and then it is going down everywhere from there on. That is what, if I just sort of superimpose this, that's what we said at x equal 1. It's going up to the left and down to the right of the point corresponding to x equal 1, which is this point, 1 comma 1 over e. And oftentimes I'll write right on my graph that it's a local max, so that I don't lose track of that as we add more detail and information to this graph. I know this has to be a high point, and I know whatever detail I add to my graph, however much more accurate I make it, it's got to go up till I hit that point, and then it's got to go down from then onwards. Okay, well, the next thing we're going to do is add another quality to our graphs. Rather than just this rough behavior where the function goes up, where the function goes down, we're going to add the concept of concavity. And that has to do with sort of how the function curves as it goes up and how the function curves or curls as it goes down. And so let's go ahead and look at that next.